The directions say to determine whether the sequence converges or diverges. If it converges, we are going to find the limit. In example 1, we have a sub n is equal to 3 plus 5n squared divided by n plus n squared. And what we're going to do is we're going to look at the limit as n goes to infinity of a sub n. But this is the limit as n goes to infinity of 3 plus 5n squared divided by n plus n squared. The highest degree in the numerator is 2. The highest degree in the denominator is also 2. And so what we're going to do from here is we're going to factor out an n squared from the numerator and also from the denominator. And so when I take out an n squared, what I have left is 3 over n squared plus 5. And that's inside those brackets there. And when I take an n squared out of the denominator, I get 1 over n plus 1. So if you notice, the n squareds cancel. As n goes to infinity, 3 over n squared goes to 0, and 1 over n goes to 0. And so what we have left is 5 over 1. And so therefore, we can say the sequence a sub n converges to 5. Right? Because 5 over 1 is 5. So that's how we do example 1. Let's take a look at example 2. Suppose a sub n is 3 to the n times 7 to the negative n. But that can be written as 3 to the n over 7 to the n, because remember the law of exponent that says a to the negative n is equal to 1 divided by a to the n. But that can be written as 3/7 all raised to the nth power. The limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of 3/7 to the n, and that's equal to 0. And the reason why is because the absolute value of r is equal to 3/7, which is less than 1. And so what that tells me is that the sequence a sub n converges to 0. That's example 2. Now, let's take a look at example 3. Suppose a sub n is equal to the square root of 1 plus 4n squared divided by 1 plus n squared. And so what I'm going to do is I'm going to, within the radical, factor out an n squared from the numerator and an n squared from the denominator. And when I do, I get the square root of n squared times 1 over n squared plus 4 divided by n squared times 1 over n squared plus 1. And so if we look at the limit as n goes to infinity of a sub n, this is equal to the limit as n goes to infinity of the square root of n squared times 1 over n squared plus 4 divided by n squared times 1 over n squared plus 1. Notice how the n squareds cancel, and I'm going to slide this limit inside the radical. And what we end up getting is the square root of the limit as n goes to infinity of 1 over n squared plus 4 divided by 1 over n squared plus 1. But if you notice, as n goes to infinity, 1 over n squared goes to 0. So what we end up getting is the square root of 4 over 1, but the square root of 4 over 1 is equal to 2. And so the sequence a sub n converges to 2. And that's essentially example 3. Let's take a look at example 4. Suppose a sub n is negative 1 to the n divided by 2 times the square root of n. A sub n is equal to negative 1 to the n over 2 times the square root of n. But if I take the absolute value of a sub n, I get 1 over 2 times the square root of n. The limit as n goes to infinity of the absolute value of a sub n is equal to the limit as n goes to infinity of 1 over 2 times the square root of n, and that's equal to 0. So notice here, we got the limit as n goes to infinity of the absolute value of a sub n equals 0. And if the limit as n goes to infinity of the absolute value of a sub n equals 0, then the limit as n goes to infinity of a sub n must also equal 0. That's by a theorem in your book. And so therefore, the sequence a sub n converges to 0. And that's example 4. So let's take a look at example 5. Suppose we have a sub n is 2n minus 1 factorial divided by 2n plus 1 factorial. Recall, n factorial is equal to n times n minus 1 times n minus 2 times n minus 3 all the way down to 3 times 2 times 1. Now, one thing I want you to know about the factorial is we define 0 factorial to equal 1. That's by definition. So let's take a look at a sub n, which is equal to 2n minus 1 factorial divided by 2n plus 1 factorial. If I write out this whole thing, we get the following. In the numerator, we get 2n minus 1 times 2n minus 2 times 2n minus 3, all the way down to 3 times 2 times 1. In the denominator, we get 2n plus 1 times 2n times 2n minus 1 times 2n minus 2, all the way down to 3 times 2 times 1. But if you notice we have a 2n minus 1 in the numerator, we have a 2n minus 1 in the denominator. We have a 2n minus 2 in the numerator, we have a 2n minus 2 in the denominator. So every factor in the numerator will end up going away because there's something in the denominator that will cancel it out, so to speak. So what we're left with in the numerator is a 1, right? And if you want, we can cancel the 1, but there's still a hidden 1 up there. It's right here, okay? And what we have left is 1 over 2n plus 1 times 2n. And if I look at the limit as n goes to infinity of a sub n, this is equal to the limit as n goes to infinity of 1 over 2n plus 1 times 2n, and that's equal to 0. And so therefore, the sequence a sub n converges to 0. Example 5. Now, let's take a look at example 6. A sub n is equal to 3 plus 5n squared divided by 1 plus n. Now, let's watch this because the highest degree in the numerator is a 2. The highest degree in the denominator is a 1. And so what we're going to do is we're going to factor out an n squared from the numerator and an n from the denominator. And when I do that, I get n squared times the quantity 3 over n squared plus 5. And then in the denominator, I get n times 1 over n plus 1. And so a sub n ends up being n times 3 over n squared plus 5 divided by 1 over n plus 1. Notice n can't be 0. So the limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of n times 3 over n squared plus 5 divided by 1 over n plus 1. But as n gets large, 3 over n squared goes to 0, and 1 over n goes to 0, right? And so what we get is infinity. And so what that tells me is that the sequence a sub n diverges. Not all sequences converge. It just so happened that the first 5 examples we chose converged. So, all right. This one's a really good question. We're going to look at example 7. And it says to find the limit of the following sequence. Now, watch carefully here. The first term of the sequence is square root of 2. The second term of the sequence is the square root of 2 times the square root of 2. And then the third term of the sequence is the square root of 2 times the square root of 2 square root of 2. And it keeps going in that pattern. Now, I'm going to rewrite this in the following way. Now, keep in mind something, that the square root of 2 is equal to 2 to the 1/2 power. Okay? So on the second line, the first term of the sequence can be written as 2 to the 1/2. The second term of the sequence can be written as 2 times 2 to the 1/2, all raised to the 1/2 power. The third term of the sequence can be written as 2 times the quantity 2 times 2 to the 1/2 to the 1/2, all raised to the 1/2. And so you can see that it gets pretty complicated. And now from here, I'm just applying laws of exponents. So on the third line, the first term is 2 to the 1/2. The second term is 2 to the 1/2 plus 1/4. Okay? That's just applying the laws of exponents to that second term. The third term is 2 times 2 to the 1/2 plus 1/4, all raised to the 1/2 power. And really what I'm trying to do is get you guys to see a pattern. Now, on the next page, this is what we end up getting. We get the first term is 2 to the 1/2. The second term is 2 to the 1/2 plus 1/4. The third term is 2 to the 1/2 plus 1/4 plus 1/8. The fourth term, and I'm going to add something to this in a minute, will be 2 to the 1/2 plus 1/4 plus 1/8 plus 1 over 16. Okay? See, that's really the fourth term of the sequence. And then what I'm going to do is go dot, dot, dot from there. Now, what we want to do is we want to look at the kth term of the sequence. Now, the kth term of the sequence is 2 to the 1/2 plus 1/2 squared, all the way through until 1/2 to the k. So what we're doing is we're summing the first k terms of that exponent. And then what I do is essentially the following. I can rewrite this as 2 to the 1/2 times the quantity 1 minus 1/2 to the k divided by 1 minus 1/2. Now, let's take a look at something. If we look at r plus r squared plus r cubed all the way through until r to the n, that can be written as r times the quantity 1 plus r squared all the way through until r to the n minus 1. But we can write this as r times the quantity 1 minus r to the n divided by 1 minus r. And note here, r can't be 1. And so watch what happens here. Notice how the 1/2 here cancels out that 1 minus 1/2 in the denominator. And what we end up getting is 2 raised to the 1 minus 1/2 to the k. The limit as k goes to infinity of a sub k is equal to the limit as k goes to infinity of 2 to the 1 minus 1/2 to the k. And so what I can do is then write it as 2 to the limit as k goes to infinity of 1 minus 1/2 to the k. And this is equal to 2 to the first, which is equal to 2. And so the limit of this sequence ends up being 2. It's a really, really interesting problem. Now, let's take a note of something here. So here's the claim. We're gonna prove this. The claim is 1 plus r squared all the way through until r to the n minus 1 is equal to 1 minus r to the n divided by 1 minus r. And this is where r doesn't equal 1. You need to know this for the geometric series. So let's go through this. Let S equal 1 plus r squared all the way through until r to the n minus 1. Multiply both sides by r. So rs is equal to r plus r squared plus r cubed all the way through until r to the n. So S minus RS. So if I subtract the two equations, I get the following. S minus RS is equal to 1 plus r squared all the way through until r to the n minus 1. And I'm going to go minus, and then I get r plus r squared plus r cubed all the way through until r to the n. But watch what happens here. Notice how the r's cancel. The r squareds cancel. R cubed will cancel the term after r squared. R to the n minus 1 will cancel the term before r to the n. And so what we have left is the following. Factoring out the s, I get s times 1 minus r is equal to 1 minus r to the n. Dividing both sides by 1 minus r, I get s equals 1 minus r to the n divided by 1 minus r. So therefore, 1 plus r squared plus r cubed all the way through until r to the n minus 1 is 1 minus r to the n divided by 1 minus r. It's an incredible identity that I would absolutely remember. So I thought it would be worthwhile to show you that result at the end of this video. Okay, I hope this is helpful. That'll conclude this video where we determined whether a given sequence converges and diverges or diverges. So, all right, thank you.